In the base catalyzed version of the Aldol reaction, an aldehyde reacts with a catalytic amount of hydroxide ion. So by catalytic amount, I mean there's not a full equivalent. All right, so if there's 1 mole of the aldehyde, there could be 1/10 of a mole of the hydroxide as the catalyst to make this reaction take place. And the product is the self-condensation, and what you'll wind up with is an aldol. So aldol is not someone's name. The aldol is what the product is. It's an aldehyde with a oxygen hydroxyl group in it, an aldol, and that's where the aldol name comes from. So this is the basic thing. And what I want you to recognize in this is the condensation. 2 of these molecules come together. So you could see one of the components is here. That's one of the starting materials that we have. And this is the other portion of it. So the same number of carbons, 1, 2, 3. 1, 2, 3, that's the one piece. And the other one is 1, 2, 3. That's the second piece in this. And now what we're going to do is we're going to go through the mechanism of this reaction. Okay, so let's look at the aldol reaction. So we're using a catalytic amount of base. And we get the aldol product, which is going to look like this. All right, so let's walk through the mechanism. So the reason this reaction works is because the alpha hydrogens, the alpha position is right here to the carbonyl, has acidic protons on it. So there's 2 of them. I've only shown the one that we need to do this reaction. And what the hydroxide ion does, it acts as a base. It attacks that acidic hydrogen, takes it off, and gives those electrons to the carbon that it was attached to. So what we wind up with here is a negative charge on the carbon, right? Those 2 electrons from the bond. And we also wind up with a water molecule that we've made from this reaction. The base takes up the hydrogen, becomes water. All right, there's a resonance structure for this, and it's a reason why these protons are acidic, the alpha protons, and we can distribute that negative charge to the oxygen. Remember, if I could spread out charge, it makes it more stable. So this is the enolate, right? And the enolate is a nucleophile, right? It's negatively charged, it has extra electrons, and it acts as a nucleophile. What it reacts with is another molecule of itself. So I'm going to erase this. And if I draw the other molecule, so one molecule will react as a nucleophile, the enolate, where I'll attack the carbonyl. And this one is going to react as the electrophile in the reaction. So let's just draw this without moving too many bonds around. Excuse me for forgetting that hydrogen. So we wind up with the O minus here, the hydrogen from the aldehyde, and the ethyl group. All right, so I have the O minus. We have water floating around in this reaction now. And what happens is that'll pick up a hydrogen from the water. And what that does is it's going to generate our hydroxide catalyst again. This is why we don't need a full equivalent, right? We use up the hydroxide to make water, and then water reacts to re-give back the hydroxide ion, and it keeps on continuing the cycle. And if we redraw this, we'll get the compound that we have shown here. Okay, in the next slide, I'd like to talk about the possibility of a mixed aldol reaction. So if we have 2 different aldehydes reacting together, remember in the aldol reaction, one is a nucleophile and one is an electrophile. So we could have 2 possibilities here for this. If I react this with a catalytic amount of base, I could have A and B, reacting with each other or reacting with themselves. So let's talk about the self-condensation first. If A reacts with itself, what we're going to get is, again, the same aldol product that we had on the previous page. I'll wind up with something that looks like this. Right? And this is A with itself. Right? I could also have B reacting with itself. And if I draw that product, I'm going to get the aldol that looks like this. Right? And this will be B with itself. Now we could also have A reacting with B. But not only do I have A reacting with B, I could switch which one's the nucleophile and which one's the electrophile. Okay, so in the first example, I'm going to draw the product, and let's see if we can figure out which one this is. Okay, so in this one, this is A reacting with B. Okay, and in this case, if we look at it, this component is B, and it got attacked, right? This is the one that actually reacts at the carbonyl carbon. So this is B as the electrophile. And in this case, you could see A over here was the nucleophile. All right. And the other option could also be found too. I could have A reacting with B, but we're going to shift which one's the nucleophile and which one's the electrophile. So if I do that, I will draw the product. Okay, so let's see if we can figure that out. We'll do this one in green. So this will be component B, which is the nucleophile portion of it, and this will be component A, which is going to be the one that gets attacked, the electrophile, in this reaction. So drawing that out, I have A as the electrophile, and B as the nucleophile. All right, so a total of 4 possible products. Okay, with this, we could also do elimination reactions. If I take any one of the aldol products and treat it with either strong base or acid and heat it, what I'm going to get is an elimination reaction. So let's look at the elimination. We're really eliminating water from the aldol reaction. The OH is going to be a leaving group in this. So let's draw one of our aldol products. Okay. And what's going to happen here is if I treat this with base and heat it, what's going to happen is I'll wind up making alpha beta unsaturated, alpha to the carbonyl, beta to the carbonyl, and the double bond is the unsaturated. So there's an alpha beta unsaturated carbonyl. Okay, so how is this happening? Let's go through the mechanism. So again, acidic hydrogens here. I react with OH minus. I could attack to form water, and the hydrogen electrons will go to making the hydroxide group eliminate. And what I'll wind up with is this plus water as a final product. So the first arrow takes the hydrogen off, forms the double bond between the alpha and beta carbons, and that forces the elimination of OH minus as this. So we regenerate our OH minus as we do this reaction. We're making water and regenerating OH minus from the reaction. Okay. This could also happen under acidic conditions. The mechanism is a little bit more complicated, and I'll go through this. So this is base catalyzed, our base reaction, and we'll do the acid reaction over here. So let's redraw our aldol product. Okay, so if I treat this with acid, H3O plus, and heat, I'm going to get the same alpha beta unsaturated compound. So let's go through the mechanism here. First thing that's going to happen when we have acid present is we are going to get protonation of the alcohol. We're going to turn that alcohol into a leaving group. So if I attack here, and again, this is an equilibrium reaction. The heat is really what drives this reaction to completion. All right, so we get this water set up to be a leaving group. Okay, so what's going to happen here is what I'm going to do is I'm also going to protonate. Let's pause. Okay, and then we can get the water that's floating in around here to take that hydrogen off and eliminate the water. So we regenerate our acid, we regenerate H3O plus, and we also generate water as a leaving group. All right, so water is always a byproduct of this dehydration reaction.